Well, you've officially made it to the last video of the quarter, and we are going to work on 2 more exercises, and then you'll be done. So in this video, we're going to look at another rational inequality, but in this case, we have a number on the right-hand side of the inequality. It's not a 0. And so remember, we always want a 0 on one side of the inequality and all the other stuff on the other side. Because of that, I'm going to subtract 1 from both sides, and I'll rewrite it. 2x plus 1 over x plus 6 minus 1 is greater than or equal to 0. And now remember, you need to get a common denominator. We can rewrite this as just x plus 6 over x plus 6 because that's equal to 1. And then combine the numerator over one matching denominator. So we have 2x plus 1 minus x minus 6, distributing that negative through, don't forget that part. And then it's all over x plus 6. Now I'm going to combine those like terms in the numerator, and I'll have x minus 5 all over x plus 6 is greater than or equal to 0. Now again, I could use sign checks with a test value, but it's really faster just to set those two binomials next to each other and say where are they greater than or equal to 0, because the rules for multiplication and the rules for division of signed numbers are the same. The outputs will come out the same. So x minus 5 times x plus 6, my two zeros would be at 5 and at negative 6. So I'll go ahead and note that it's a parabola opening upwards with zeros at negative 6 and at 5. So if I sketch this, I'll have positive values to the left of negative 6, negative values between negative 6 and 5, and positive values again as outputs from 5 to infinity. Remember, I'm dotting this line because this is not necessarily the shape of the rational expression if we were to graph it as a function. But it does help me identify where the function is above and below the x-axis. So since I want greater than or equal to 0, and the vertical asymptote at negative 6 cannot be included, we'll put a hole at negative 6 where the vertical asymptote exists. And that value can't be included no matter what, because it would make the denominator undefined. So my interval for which the rational inequality is greater than or equal to 0 is on the interval from negative infinity to negative 6, parentheses on both sides, union, and now we can include this 5 over here because that doesn't include the denominator. So bracket 5, comma, infinity, close parenthesis. And we are officially on the last question. We have x plus 4 times x minus 1 all over x plus 3 is greater than or equal to 0. Again, we're going to sketch really quickly, identifying the zeros and the vertical asymptotes. We have a vertical asymptote at x equals negative 3, and we have roots at x equals negative 4 and at x equals 1. So let's make note of these things. We have a vertical asymptote at negative 3. We have a root at negative 4. And we have a root at 1. Now we have to figure out how this function is positive and negative. Remember, if we list all the binomials next to each other, we'll have 3, or a cubic, so we know its shape has end behavior leaving on the bottom left and leaving from the top right. And it wiggles through 3 values, -4, -3, and 1. So my values will be negative, positive, negative, and positive. Again, that's not the shape, it's just showing where the graph is above and below the x-axis. We want where the function is greater than or equal to 0. It's where these dotted lines are above the x-axis. So the interval for which this function is greater than or equal to, don't forget the or equal to, will be open bracket -4 to -3, close parenthesis because we can't include the vertical asymptote, union because there's a gap in where the function is positive, bracket 1, comma, infinity, close parenthesis. That's the interval for which that inequality is true. And you are done!